what I call the study guide number 3. Study guide number 3 is going to give you a guidance to the links in the web page. I'm going to give you a little explanation, short explanation about that. And we are going to look at the assignment, which in this case would be the first computer simulation or putting together an entire system, in this case a mechanical system. So let me disappear from here and continue with the presentation. So in here we have several links that are on the web page, and they are designed to give you a guidance, like this one is to do the computer simulation, an introduction to the software. See here, you can see my cursor, right? An introduction to the software CAMG MATLAB. Also, if there is an interface of CAMG to the Advanced Continuous Simulation language, which we should see. And then there are procedures for modeling mechanical systems here. And the other procedure that we have is for modeling electrical systems. So you have in here. Okay, there we go. This is for electrical systems. The idea here is that you have a guidance of what's on the web page on this topic, and also a guidance on your assignment. So we'll look at the links in a moment, but the assignment here, homework number 3, which would be due on March 17, week from today. You have these problems to do, and then I'm asking you to generate the entire bond graph model of the system. I would like you to write the constitutive laws, the constitutive equations of each element following the power flow, with the idea that now if we present a system using a bond model, we should be able to obtain its equations. Yes?
Your quiz is on the 24th, is this screen right? That was 2014.
Oh, so it needs to be 2015. See, we won't go back a year, but so this is the homework, and then you have a computer assignment on March 19, which we're gonna show you in a few moments. And finally, plan ahead for the quiz on March 24, 2015. See, I don't restrict that on the here because I have to go through Dreamweaver to do just a little correction and upload the file again. So it's not that easy. But in any case, let's go over here and take a look at what we have in here with the computer simulation introduction to the CAMG MATLAB system. And here, this is the approach that we use. First of all, we have a physical system in here, and then we look at an engineering model next, and then we have this will be a sketch of what the system is made of. You have this bond graph, which is the representation of the system itself. That bond graph is entered into the CAMG software, and we go to either ASL or MATLAB. any of these. So we have in here after doing that, we can produce plots and graphs, and that will help us analyze the results. We have a bit of a comparison in what the conventional approach is and what the CAMG approach is. This is the approach as presented by Norman Neese in his control engineering book. It says determination of the physical system specification from the requirements to you draw a functional block diagram. But you have to transform the physical system into the schematic and then use the mathematical model. So you write the equations and then you write your block diagram. And number 5 says reduce the block diagram to a closed loop system. Well, okay. And then analyze the design. In this new approach, you have to identify the physical system elements using words to identify what they are, then draw the bond graph and enter this into CAMG. Once CAMG takes over, it generates the differential equations and the state matrices in symbolic form in the form of M files. So CAMG basically hands delivers the system to MATLAB. And then we use MATLAB to analyze the design. Okay. Okay. We have this system in here that we can say this is a basic system, a non-electrical system in here, and then you write the equations and then you have it in the second order form here. For an electrical system, you could just apply the Kirchhoff's laws around a loop, and this one you will have to use Newton's equation. So once you have it in the equations in second order form, like the shown above, like here, see, like this, then you can transform it into first order differential equations, like this. You can obtain the block diagram either from the second order differential equations or from these ones. However, it requires the skill of having done the derivation. However, here, if we use the bond graph model, it's a simple representation of the system, which the symbols reveal the type of elements that they represent. Like, for example, this source of effort is this one. Then we have an inductor, which is this one, a capacitor, which is this one, and a resistor, which is this one. And you have a situation on the mechanical side that the velocity is common to all this, like the current was for this. But for these other ones, the velocity is the same. For the inertia element, that is the M element, you have this K element, which is the C element, the quickness, and you have this one, which is the damper. If you consider this one single system, all the bonds will be attached to that one. But because it's a one junction, expect only one bond to set the flow. In this case, you have the system. This symbol represents the mass. This represents the force. This represents the mass. C is the spring, and B is the damper here. See, here we have the inductor over here, then the C element over here, and then the R element over there, the resistive element. So, having done this, I can show you that CAMG can produce the state space form. In this form, the equations. We will see as we develop this topic, how do you obtain these things? And then you enter in the CAMG. Okay. What you see on the left-hand side is, well, I have drawn it just a sketch, but this is the actual bond graph model as entered into the CAMG software. I just superimpose the other pictures in here for explanation and clarity purposes. So one can relate this odd shape bond graph to this system. Okay, so here's what CAMG is going to do for you. CAMG is going to generate the schematic. CAMG is going to generate the mathematical equations, but you have to enter the bond graph, and it will give you the state space equations, symbolic system matrices, and the simulation emphasis. Then we add the parameters, the control blocks, the nonlinear part. MATLAB will do a time analysis or frequency domain. Then you have the graphical representation, which is what we would like to see for understanding this. So, using the program, we'll create a bond graph model in graph form. We produce MATLAB M source code files for systems represented by bond graphs. Obtain the general symbolic transfer functions, and also model physical and control systems combining block diagrams and bond graphs. Okay, once the program is run, you have two possibilities of the sets of equations. One is the MATLAB type equations, the other one I call the ACSL type equations. Both sets are totally equivalent, both sets solve the same problem. Difference is that the system on the left-hand side is being sorted out. In other words, you do not have dependencies that may affect the execution of the program later. But in here, there is a logical order for the one on the left, and there's just no logical order, just a listing on the ACSL side. The reason is that the ACSL doesn't care about which statement was defined first. It cares about the whole thing, and therefore you could have it in the way it's on the right hand side. You could organize all the efforts in one directory of folder. You have all the flows, and then the differential equations, which are those dp2 and dq so forth. So that's what this is. What you will get? You will get CAMG-mod, which is a file that controls the simulation, defines the parameters, the input vectors, the initial conditions, all those things. CAMG-EQU is the MATLAB function which contains state space form in symbolic matrices, and you will CAMG-SYM file, which are the system A, B, C, and D matrices in source code form. Here's a little bit of an introduction of the CAMG-mod.m file. In this particular case, we are going to, you see, the computer gives you an opportunity to initialize the values right here, to specify what your inputs are, the initial condition vector, and then you have simulation time control, meaning you have the TF, T0, and TF. It's time, the solution of differential equations, branch cut integration routine, or you could use 4 or 5. There's others also. This commands the MATLAB to return the values of P and Q based on the way we set it up, yeah. And then the plot and results. This is the way it's structured. They continue a little bit on the equation side, but this is what's important. Here you have the computer simulation of the velocity, and in this case initial condition was 0. Okay, so this is the way we do the computer simulation once we have a file that describes the system and is clear on the objectives here. Any questions about this? This is the symbolic file, which is delivered to MATLAB, and it contains in here the differential equations. Right there, there's one equation, there's the other one over here. And finally, we can do the plots in the frequency domain, as well as the body plots, you know, using frequency domain, as well as the step response, which is the time domain. So you see both of those in there. Okay, let's stop now that we have this overview.